Hi, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. Today I want to cover hybrid-ring duplexers. If you find this particular video helpful, please click on the like and subscribe to the channel so that you can get notifications when new videos come out. Hybrid-ring duplexers depend on a cable harness with very specific lengths of coaxial cables, a nulling cavity, and a capacitive tuning stub to set its pass and reject frequencies. Now, because it depends on the lengths of the specific cables used in the rings for its tuning, its performance will significantly suffer if it's used at a frequency further than 3% away from the designed center frequency. So for example, suppose you were to be able to get a hybrid ring duplexer that was originally designed for the 162 megahertz commercial band, and you wanted to use it down in the ham band. Well, it would be essentially good for 162 megahertz plus or minus 3%. So it would be good from a 157 to 167 megahertz. You couldn't really use that one down in the ham band without having to redesign the cable harness. On the other hand, if you had one that was designed around 146 megahertz, now its useful range would be 143 to 151 megahertz. But of course, the closer you get to the design frequency, the better the performance you get out of the duplexer. Now, in order to best understand the tuning procedure, it's good for us to understand some of the theory behind how these duplexers work. And for that reason, I'm going to first go into what is the theory behind how these hybrid ring duplexers work, and then I will go into specifically how to tune one. Now, I don't have a hybrid ring duplexer to be able to demonstrate how to do that, so I'm going to have to do it by explanation and with some pictures along the way. And a note, I have included links to all these documents, a detailed description of how to go about tuning these hybrid ring duplexers, as well as the theory behind them. And then also an old Sinclair document from 1966 on the theory and tuning of these hybrid ring duplexers. I've included links to that in the description for this video, so you can review these in printed form as well. Now, in order to best understand the tuning procedure, it's good for us to understand some of the theory behind how these duplexers work. And for that reason, I'm going to first go into what is the theory behind how these hybrid ring duplexers work, and then I will go into specifically how to tune one. Now, I don't have a hybrid ring duplexer to be able to demonstrate how to do that, so I'm going to have to do it by explanation and with some pictures along the way. With that, let's go on into the theory. So, we want to find out how these hybrid ring duplexers do what they do. Well, at the very core of how they work are two distinct principles. The first principle is, if I have a signal like this, and I add that to a signal that is like this, if these are the same frequency and the same amplitude, the resulting signal is, well, nothing. So two signals that are the same amplitude, the same frequency, but 180 degrees out of phase to one another, added together, gives us nothing. The second principle that is at play in these is that if I have a piece of coax here that is electrically 1/4 wavelength long at a particular frequency, then that means that if I were to short this side or have a very low impedance at this side at that frequency, then at this particular frequency here, F1, this and down here, this is a low, this would look like a high impedance. And vice versa. If I left this side sitting wide open, at this frequency F1, this side looks like a low impedance. Those are the two principles that make these duplexers work. So, with that in mind, let's go into understanding the initial steps of what makes these duplexers do what they do. So suppose I had a T here, and I had another T down here. Okay, so here's my connection T. Here's my connection T. And I have signal that goes around like this. Now, I put a signal in here. This is 1/2 wavelength long at a particular frequency. Let's call it F0. And this side over here is 1 wavelength long at this particular frequency, F0. So I have my signal, F0, going in this side. It travels through this 1/2 wavelength long piece of coax. It travels through this 1 wavelength piece of coax, and at this point right here, this path right here is supplying something that is in phase with our F0. On the other hand, we have this 1/2 wavelength piece of coax, and here at this point we would have a signal that is 180 degrees out of phase. And like I said, if you have two signals that are the same amplitude and the same frequency that are exactly 180 degrees out of phase with one another, then the resulting signal coming out our port here is nothing. Now that's assuming that we can cut perfect pieces of coax and have them exactly 1/2 wavelength and 1 wavelength long. But we want to have a pass frequency. So how are we going to do that with this kind of a situation? Well, the best way to do that is to have some means of eliminating one of these two paths at the pass frequency. So what they do is this. They take this 1/2 wavelength piece of coax and they cut it in half, and they put a T in here, and now they add to that a null cavity, a shunt cavity. So how a shunt cavity works is that at its frequency of resonance, the impedance at this spot right here, let's say it is resonant at F1. At that frequency F1, this looks like a very low impedance. Essentially what it's doing is it's taking this leg here, and at the quarter wave point from each side, it is shorting out the signal to ground. Now remember, we have 50 ohms over here, and we have 50 ohms over here, because this is now shorted, essentially shorting it to ground. This is now a low impedance, presenting a high impedance here, and a high impedance here. And so this, because this is now a high impedance at the end of this cable here and here, it's not really affecting this. but it is taking this and essentially taking that signal and shorting it to ground here, eliminating this side. So that means that for the band pass at F1, this leg is eliminated, and band pass, our signal just runs around the one wavelength side of things. Well, you know, this is all well and good, except again, we cannot create a perfect wiring harness. No matter how hard we try, this is not going to be exactly the right length, and these are not going to be exactly the right length, and this is not a perfect shunt cavity, so it's not going to be exactly what we would necessarily want to have. So in order to make this adjustable so that we can make it so that the signal that enters here at our reject frequency F0 is exactly 180 degrees out of phase at F0 for our reject frequency, what we do is we come over here and we add a capacitive tuning stub. So what this capacitive tuning stub essentially does is it changes the apparent electrical length of the one wavelength side of this loop so that we can move these phases around so that they finally coincide. So on one hand, we have the pass frequency at F1 with this shunt cavity eliminating this side of the loop, and then we have this capacitor on this side of the loop making it so that we can vary the electrical length of this side so that at F0 these are 180 degrees out of phase with one another. Now, an important point, remember that this was 1/4 wavelength. This one is 1/4 wavelength, right? Well, this one has to add, this adds up to 1/2 wavelength. This side has to be 1 wavelength long, and so this right here, this portion right here is 1/4 wavelength, electrical length. That takes in consideration the velocity factor of the coax itself. And then if this is 1/4 wavelength and this is all supposed to be 1 wavelength, then this one has to be 3/4 of a wavelength. So we still end up with a 1/2 wavelength on this side, 1 wavelength on this side. This allows us to vary the apparent electrical length of this side so that we can get our phases. This guy allows us to eliminate this part of the ring at the pass frequency F1. So that's kind of how the whole thing works. This is a shunt cavity that's tuned to the pass frequency, and then this capacitor here allows us to tune for the reject frequency. So simple as that. Now let's go into how to actually tune a hybrid ring duplexer. Before we can begin actually tuning a duplexer, we need to get ready for the test. Now, all of these things have been covered in the last video, so I don't want to cover them in detail here. I do want to mention them by way of reminder, however. The first thing is to make sure that you have the right test equipment. Now, because hybrid ring duplexers can have rejections up to 100 and 120 dB, clearly you need to have some good quality test equipment, a spectrum analyzer with a dynamic range of at least 100 dB, along with a directional coupler. The spectrum analyzer has to have a tracking generator on it as well. So the spectrum analyzer with a tracking generator with a dynamic range of at least 100 dB with a directional coupler. Or you can use a vector network analyzer, or VNA. Again, these little mini VNA Tinys, these nano VNAs, do not have the dynamic range necessary to tune one of these effectively. So they're kind of off the table. You need a higher end vector network analyzer. So the next thing is we need to understand what we're adjusting. Now in the theory portion of this whole thing, I talked about how the plungers adjust for the return loss, which affects the pass frequency, and the capacitors adjust for the reject frequency, and that is true here. So that is what you're going to be adjusting. So the next thing is to make your plan. You need to have a plan. You need to know what you're tuning for. You need to decide which side is going to be the high pass side, which side is going to be the low pass side, which is going to be the receive side, the transmit side. You need to decide on exactly which frequencies you're going to be tuning it for. And I highly recommend that you take a little pad of sticky notes and write down the pass and reject frequencies for each of the hybrid rings and stick them on their associated cavity. That way you don't have to try to remember. It's amazing how many times you can end up having to ask yourselves that question over and over again. Okay, I'm tuning this. This is the pass is what, but if you have it on little sticky notes, it just eliminates all that for you. And then lastly, you have to choose a tuning track. This is kind of like part of making a plan. Choosing a tuning track. Now there are what I call two tracks. There's the first track here, which is for those duplexers that are a complete unknown to you. Maybe someone gave you a duplexer and you have no idea what it is. We can find out where it is tuned now, but track one is for when you discover where it's tuned, and it's tuned far afield of where you plan on using it. This at least gives you a way of knowing that, and then doing the initial tuning, getting things kind of close in and together so that you can go on and do the final tuning. And this is a significant thing when this is far, far afield where your frequency where it's actually tuned. Number two is if it's already tuned, let's say the duplexer is coming from a repeater site and it's tuned to that repeater frequency and someone just wants you to tweak it up. Well, number two is like the final tuning of the whole thing. So how do we know where it's tuned? Now I go over this in detail in the last video, so I'm just going to show you by way of reminder how we discover where that is tuned. So to begin with, this is just kind of a ballpark thing. You don't need to go through all the calibration procedures and everything in order to do this with your VNA, because this is just ballpark. Where is it approximately? And so here I'm just going to draw a big block, and we're just going to call this a duplexer. And it's got 3 ports. It's got the antenna port, and it's got a high pass port and a low pass port. So what you're going to do is you're going to take if you're using a VNA, you're going to terminate this port with 50 ohms, and then you're going to connect your tracking generator, or your port 1 of your VNA here. If you're using a spectrum analyzer, this would be your tracking generator output. And then over here, you connect this to port 2 of your VNA, or to your signal input of your spectrum analyzer. You set up your vector network analyzer to do through or an S21 measurement. And then what you're looking for on the screen on both of these is you're going to see 2 little dips. And what you're seeing here are the reject frequencies of these two hybrid rings here, because the signal passes through here, across through here, and out here. So you'll see two negative pips if they are tuned to a specific pair of frequencies. It is possible, if someone has been messing with this and it's way out of tune in weird ways, you might see a third pip in here. You might even see a fourth pip in here if the two halves of the high pass or the two halves of the low pass are tuned to different frequencies. So then you look at these frequencies where these pips occur, and then you decide, are these far enough afield of where I want to tune my duplexer to go to track 1 and just basically start from scratch and make sure that everything is as it should be. So, having done all that, and I encourage you to go back to the first video and review the steps in detail there. But now we're going to turn our attention to how to actually do the tuning. We're going to start with track 1, initially tuning a hybrid ring duplexer when it is far afield of where you want it tuned. So now we're going to talk about actually tuning the hybrid ring duplexer. This is a diagram of what you physically actually have there. You have, this is one hybrid ring, and it is connected to another hybrid ring down here by L1, and these two here work together to produce the effect of this side, and then this is connected through this T to this side, and these two hybrid rings work together. So this side could be the high pass side, this side could be the low pass, or vice versa, but their common is the antenna connection here. Now the first thing you want to do is make sure that you mark everything. Specifically, you want to mark the capacitor for hybrid ring 1 in such a way so that it will always go back to hybrid ring 1, exactly the way it was there, and so on. Hybrid ring 2, same thing. Hybrid ring 3 and 4, same thing. You also want to mark these lengths, because these lengths between the individual hybrid rings are also critical lengths. They are chosen and tuned and specific for the tuned frequency of the overall system. Same thing with these two guys down here. So mark everything. Once everything is marked, then you're going to remove L1, you're going to remove L2, and you're going to disconnect this part of the harness where L3 connects to hybrid ring 2 and where L4 connects to hybrid ring 4, and remove it. And what that ends up doing is completely isolating 4 distinct hybrid rings. And now we can go into the actual tuning process of each individual hybrid ring. Now that you have each hybrid ring isolated, you want to loosen the set screws, nuts, whatever is holding the plunger from being able to move. You want to loosen those so that you can easily move those. And then once you have that done, you want to actually take the capacitor here and you want to disconnect it right at the T. So you're maintaining the cable that's connected to the capacitor, you're maintaining the capacitor, you're just disconnecting the capacitor. So now what you're left with is the hybrid ring by itself and the cavity connected to the hybrid ring. Now you're going to connect up your VNA. You're going to connect up port 1 of your VNA here, or if you're using a spectrum analyzer with tracking generator, you're going to be connecting up the port of your directional coupler to here. You're going to be taking and putting a 50 ohm termination here. You'll leave this one unterminated, and then you're going to adjust the plunger on the cavity for the maximum return loss at the pass frequency. Okay? So you tune the cavity for the maximum return loss at the pass frequency as you're looking in here with a 50 ohm load down here and this disconnected. Once you get that, then you can reconnect your capacitor. You're going to see it shift some and retune this again to center that return loss right on your pass frequency. All right, next step is to adjust for the reject frequency. So at this point you've already tuned the cavity for maximum return loss, S11, at this port with this one terminated with a 50 ohm load. Now we're interested in the reject frequency of the whole system. Well, to do this, if you're using a VNA, you would connect up port 1 here, and you would connect up port 2 here. If you're using a spectrum analyzer, you would put your tracking generator on here, and you would put your input to your spectrum analyzer on here. And then you would tune this capacitor here for maximum reject at your reject frequency. Now, when you tune this, it can mess this up. They interact with one another, as you might expect. So after you tune this for your maximum rejection being right at your reject frequency, guess what? You get to go back, put your 50 ohm load back on here, and look at return loss here to move this until that all agrees with the proper pass frequency. Then, well, guess what? You've moved this. Now you get to go back and retune this one over here, and back and forth you go until, again, because the moment we connect this to its next guy in line, it's going to skew things some, so you don't have to get it perfectly on. You need to get it close. So once that is done, then you go on to your next one, and your next one, and your next one, tuning each individual hybrid ring as a single unit. Once you have done that, now you're going to take your two hybrid rings. Let's say this is the high pass side. You're going to take your two high pass hybrid rings, and you're going to connect them back together. Now, you will have two high pass hybrid rings like this, and you're going to do exactly the same thing that you just did over here, only now you're doing it with two hybrid rings, and you're adjusting two plungers, and you're adjusting two capacitors, and you're working to get the two different frequencies that these are tuned to so that they're all nicely lined up with one another and getting the maximum possible return loss and the maximum possible rejection at the rejection frequency. Then you're ready to go on to final tuning. But before you do, you need to reconnect all of your other cables. Connect this side up to this side and connect these cables together. And then you're ready to go on to track 2 and finalize the tuning of your duplexer. So now we enter track 2, final tuning of a hybrid ring duplexer. Well, in many ways, the final tuning of a hybrid ring duplexer is really no different than with a regular duplexer, except in the performance that you can expect out of it and the interaction that you're going to get between individual rings. You know, you tune this one and it might affect any one of them. So you know, there's more variability there. You still tune the plungers on the cavities for maximum return loss, getting everything lined up, and you still tune the capacitors. It's just that instead of a little nice little screwdriver tweak, you have a little slidey inny-outy thing to tune, and it makes it a little bit more difficult to make minute adjustments, but you can do it, and you can expect performance on the return loss at the pass frequency from -30 to maybe -50 dB, and on the rejection side anywhere from -80 to 120 dB. The closer you are to the design center frequency of the duplexer, the better these numbers are going to be, and the further away you get, the lousier they're going to get. If you're too far away, then you're going to have to redo the cable harness to get these kinds of numbers. So there you go. Now you can go and review the specifics on doing the final tuning by looking at the second video in this series. If you find this all helpful to you, please don't forget to click on the like button and to subscribe to the YouTube channel. In the meanwhile, I just want to thank you so much for watching. You take care, and toodaloots.